Good day. I'm super excited you've joined me because I get to talk about one of the coolest parts, in my opinion, of chemical engineering thermodynamics, which is flash calculations. Now, we're going to pretend it's not the 101st try, that's not a joke, of me attempting to take this video, and we're going to go through the fastest, hopefully, presentation and still squeeze this into 20 minutes because there is a lot of information that I really want to talk about here. I'm super excited, so let's go ahead and get right into this. We are talking about flash calculations. Now, what are they? Well, here's Merriam-Webster's definition. I think I have a cooler one. It's a flash calculation in my simplest terms, or in my own words, is going to be when I have some sort of container full of liquid. And that liquid obviously has some sort of boundary layer with some sort of environment of vapor. And that boundary layer is in constant vapor-liquid equilibrium. However, the flash point is when we actually change that liquid's physical properties, usually by introducing some sort of heat source, until we release enough vapor from the liquid in order to ignite some sort of flame. And that flame causes a flash, and that flash is why we call it a flash point. Now, what can we distinguish the flash point between? Well, there's two other topics, and my giant head is in the way here, so I'm going to kind of fade out of my little bubble here for a second. We got flash point is very similar to two other thermodynamic properties, being boiling point and the auto-ignition point. Now, we defined the flash point as the lowest temperature at which the vapor will go ahead and ignite some sort of source. Well, this is very close, as you may recall, to the auto-ignition temperature, which is the temperature that the vapor will go ahead and ignite the air. Now, the difference mainly between these two physical properties is the fact that the auto-ignition point will ignite without a source, while the flash point requires some sort of source. So, as you can imagine, flash points are generally tabulated at much lower than auto-ignition points. Now, the boiling point, which is also kind of confusing because there's definitely liquid and vapor happening there as well, the boiling point is going to be the point where your liquid phase is going to transition into your vapor phase due to the pressure of the environment being equal to the vapor pressure of that given liquid. So it is more of an equilibrium pressure state, whereas a flash point generally corresponds to a change in temperature. Now, obviously, the boiling point can change because of temperature as well. However, we're looking more at pressures with boiling points. How is that pressure going to affect that boiling point? Because you're attempting to get that liquid up to a high enough temperature to have it exert a pressure equal to its vapor pressure. Whereas with a flash point, you're simply raising temperature. So, as you can imagine, flash points are going to be the lowest of these 3 points, which is why I kind of included this table here, comparing some flash points to boiling points. But what exactly is the importance of flash points? Well, as you can imagine, they're going to give us our flammability ratings. And obviously, we remember these from chemistry classes and labs. They're going to tell us how flammable a fluid is. So, we describe a flash point of less than 100 degrees as flammable, or greater than 100 degrees as combustible. So I included gasoline as a flammable fluid and diesel as a combustible fluid. A combustible fluid is going to require, obviously, your combustion reactants, the main one being oxygen, whereas the flammable fluids are going to be much more likely to ignite just because of the presence of their vapor. So, I'm going to go ahead and talk about the equilibrium flash point at this point, and briefly mention the Rockford-Rice equation. I was going to derive it, and that ended up taking an infinite amount of time, and there is a video that is 40 minutes long. If you would like me to release the NOR cut, if you will, that actually has me deriving the entire equation there. But we're skipping that for now, and we're just going to talk about what the simpler problem is, and that is this PT flash calculation. So with a known temperature, pressure, and overall composition, we introduce a solvable prompt based on Duham's theorem. Duham's theorem states, or postulates rather, that for any thermodynamics closed system, we can actually define all of its intensive and extensive variables based on if we know two intensive conditions. And so in this case, obviously, that will be our temperature and our pressure, which are going to be not dependent on mass, and therefore qualify as quantities we can measure for Duham's theorem. So, moving on along to our example, which is going to take up the most of this video, I want to perform a flash calculation on a 3 chemical species mixture here. Ooh, lost my word there. So we have this system of acetone, acetonitrile, and nitromethane at these given conditions with given overall compositions. And we want to assume that Raoult's law is appropriate and determine the concentrations of their liquid and vapor phases, respectively. And we're also given the vapor pressures of the pure substances at 80 degrees Celsius. So let's jump straight into this here. I'm going to go ahead and cast my iPad here to the screen so that you can follow along with me as I go ahead and do the calculation here. So I actually have this pulled up on another screen right here, the prompt. So apologies if you can't see the prompt, but I can. So we have our system here. I'll go ahead and write the initial conditions again. We have acetone, we have nitromethane, and oh, I just messed that up. Nitromethane is actually number 3, and acetonitrile is number 2. And again, we have a temperature of 80 degrees Celsius. We'll go ahead and convert that to Kelvin real quick. So we'll add 273, and we'll say it is 353 Kelvin. And we have a pressure of 110 kilopascals. We also have an overall composition for each component. We have Z1 being equal to 0.45, Z2 being equal to 0.35, and Z3 being equal to 0.2. We are told that Raoult's law holds for this system, and we are told the vapor pressures of the pure species. So 195.75, 97.84, and P3 sat is 50.32. And all of these are in kPa, or kilopascals. So, what are we going to do? First, we want to even attempt to see if a flash point is even accessible at this point. And so the way that I'm actually going to do that is I'm going to calculate a bubble point, the point at which the liquid will release the first bubble of vapor, as well as a dew point. And by doing that, I'm going to determine whether or not the pressure is actually within the range that a flash point calculation is necessary. So we have this given pressure here at 110, but we need to go ahead and calculate our bubble and dew pressures. So let's see. The formula for a bubble pressure, well, because, well, we can go ahead and say that Zi for our bubble pressure is equal to Xi for our bubble pressure. And that makes sense, right? Basically, all of our substance is going to be liquid at this time. So, doing that calculation, I'll say the pressure bubble is going to be equal to our three components mole fractions multiplied by their saturation vapor pressures. And I will go ahead and crunch those numbers here. So we have 0.45 times its saturation vapor pressure, and we're just going to do that down the line here. And again, this is because our Raoult's law holds in this case. So we go ahead and calculate a pressure of 132.396 kilopascals. And so that is higher than the pressure, so we're already on the right track. Now let's go ahead and calculate a dew pressure. And let's see. Okay. Again, we're going to say at this point that Zi is equal to Yi. So this is for dew, this is for bubble. And again, the reason for that is that we're mostly at dew, but we're going to have one little bead of maybe condensated liquid at this point. So we're going to do basically the exact same thing. However, remember, the dew calculation is slightly different in that our formula here will be 1 over y1 over p1 sat plus y2 over p2 sat plus y3 over p3 sat, which will actually go ahead and come out to, give me just a moment here to crunch all these numbers. 0.45 over 195.75 plus we have 0.35 over 97.84 plus we have 0.2 over 50.32, which is going to give us approximately 101.52 kilopascals. Now, again, our pressure was equal to 110 kilopascals, which is actually in between our dew and bubble pressure. So a flashpoint calculation is available for this sample here, and we've just gone ahead and proved that. Now, moving on along, now that we know that we can actually do a flash calculation, what are we going to do to actually do it? Well, do, because DEW, not dew point, flash calculation. Let me make that very clear. Let's go ahead and actually sort this out here. So, let's see. Again, we were told Raoult's law is applicable to the system, so therefore, we can go ahead and actually construct a relation between the equilibrium constant and pressures. So we have defined an equilibrium constant as K in the past in chemistry class, and from Raoult's law we would say that it's equal to the vapor mole fraction over the liquid mole fraction. Or in other words, it's equal to the saturation vapor pressure over the pressure of the system. So we can go ahead and calculate that for our three components here. And we'll say K1 is equal to, well, Yi over Xi. So, or P sat I over P, rather, is what we're going to actually end up calculating. So we said P sat I for 1 was 195.75 over 110, and this is going to be a dimensionless unit here, which makes sense because our rate constant is generally unitless, and it's going to be about 1.78. K2 then will be 97.84 over 110, which is going to come out to about 0.89. And finally, K3 is equal to 50.32 over 110, which is going to be about 0.457. So there we have our 3 equations. And what we're going to end up doing with those is we need to construct some sort of material balance from which we could root solve for our moles of either vapor or liquid phase. Now, I'm just going to go ahead and pull up the equation I derived. This equation I was going to derive during this presentation. However, the time limit has kind of constrained me from doing that. So we have this equation here, which relates overall composition and rate constant to this big V is going to be moles of vapor of the system. And it comes about from a material balance, and it works for every single flash calculation that you would ever intend to do. So from that equation, I'm going to go ahead and write out our root solved equation. So it would look something like this. Our Z for each substance along with our K for each substance. So Ki, yes, so it would be about 0.78 moles of vapor times 0.78 plus 0.35 times 0.89. Oops, I missed a 1 here for some reason. Okay, and 1 minus 0.1105 V plus 0.2, which is the mole fraction, times the K, 457, over 1 minus 0.5425 V. And all of that is going to be equal to 1. Now, subtracting 1 from both sides, we can use a root solver algorithm, such as Newton's method, to go ahead and solve this. So again, another thing I was going to do was code that out on camera here. However, again, running out of time. So I'll go ahead and write the results of that root solver now. For number 1, we have the moles of vapor being equal to 7364 moles. And the moles of liquid are going to be equal to 1 minus the moles of the vapor, which is equal to 0.2636 moles. Wonderful. Now, with all that done, we can go ahead and plug back into another equation that I derived earlier, which is y1 is equal to zi ki over 1 plus 1, or rather ki minus 1 times the v. And then again, xi will be equal to yi over ki due to Raoult's law. So from all of that, again, I've already pre-crunched these numbers. Obviously, I told you how many times I've done this video. So there is my first mole fraction, Here is my second mole fraction. And actually, I went ahead and I printed these all on the slide at the end here, the summary slide. So I'll just go ahead and bring that up at this point. Let's see, boom, boom, cool. So the conclusions are going to be as follows, boom. So here is all the mole fractions for acetone, acetonitrile, and nitromethane at their flash point. And note that all of these sums will equal approximately 1. And that makes total sense because they're mole fractions. They should add up to 1. So all the x's will add up to 1, all the y's will add up to 1. I know I went about a minute or two over, but I have just had so many kicks and giggles with this project. And so I'm very happy to share it with you in pristine form right here. And I hope you enjoyed. Thanks for sticking around to the end. I've been Michael Noor. Thanks for watching.